Okay, hello everyone. As you all know, Professor Pulgar is sick this week, and I'm gonna take care of his class for this week. I'm Sebastian Martinez. I'm one of his PhD students. I also work on power systems, so I know this topic very well. In any case, you have any questions, even though I'm not the official TA of the class, since I am helping him with this week lectures, you can contact me if you have any questions. Here's my email. You can also find me on the Minkau building. I'm gonna, this is my office. You can find me there too. What is the idea of this class is to review some general numerical integration techniques. He told me that after he comes back from his problem with his sickness, he's gonna finalize the example that he was working on. But at this moment, we're gonna go on with chapter 4 straight to it. So first of all, what we need to know here is that we're gonna be dealing with some system, some power system, right? Which is gonna be modeled by this kind of equation, f of x t, x comma t, with some initial condition x of t0 equals x0. And we know that the state variables in general are going to be n state variables, and consequently our initial condition are going to be n initial conditions too. So as you may have studied already, you know that in real power systems, the amount of state variables and equations that you have to represent a real system are in the order of thousands or even more, a couple of hundreds of thousands. So this system of equations, it's actually something quite big, right? It's going to be something like this, right? It's going to be a vector equation in this fashion. So if one, this is going to be dependent on any, not necessarily all of them, but many state variables. The same for the other functions. And one of the important characteristics here is that these functions f in general are going to be nonlinear representation of the equations of the system. Those are going to include the generator, synchronous generator dynamics, controller dynamics, the grid itself, transformers, loads, any other component that is going to be related to the grid. So to get a grasp of what we're working on, this is going to be quite a big system. So just a reminder, general considerations. Before we start with this, right, with this numerical techniques. So we have power systems are nonlinear, right? Large number of states and equations. So what we need to know here is basically that since we have thousands of variables, here we cannot solve the solution of the system analytically. We have to we required some numerical solution. Since this is a nonlinear system with many state variables, many equations, so I'm going to write it down here. So the numerical solution or more so analytical solutions are most of the time prohibited. So you can't find. And why do I say most of the time? Because sometimes a linear model of the grid and the controllers and all the components, can be enough to model something that for certain studies. Yeah. So if you want a good representation of the grid, you're gonna need a nonlinear system, which is gonna lead to a numerical solution, the need for a numerical solution. So the second thing that we need to know here, it's that from numerical solutions, we need at least two things. Number one, stability, but then we're going to say stable. Number two, accurate. So stable means that the numerical solution that we're using is not going to blow up, basically. So let's put some simple example here. Let's use some simple example. So let's say this red one is the exact solution of some problem, right? Let's say this red one is going to be the approximated numerical solution. So you can have something like this, right? And that would be unstable. I'm gonna put something like that. Okay, that would be something unstable, and we don't need. We want to avoid those kind of numerical methods. And accurate, of course, is going to be that the numerical solution is going to be close to the real solution. So let's say the approximate solution minus the exact solution is going to be, let's say, low. The error between those two, the exact solution and the numerical solution, is going to, the error is going to be low. It's going to be bounded, if you will. Okay, so of course in this class we're gonna learn some of the basic numerical methods that fulfill these characteristics. However, there are some commercial softwares out there so there are commercial softwares for power systems that are they're designed to deal with this high dimensionality of the power system, their controllers, and you can do not only transient stability analysis, but also protection analysis, steady state analysis, signals analysis, and so on. So I'm going to give you some names so you can have reference. PSSE, for example, is a very famous one in the US, together with Power World. Those two are commonly used for ISOs here in the United States. However, then in other parts of the world, for example, Power Factory, Dig Silent, it's a very famous one, or ETAP. It's also another software very used for industrial models of a power system. So at least here you have 4 major names where you can consult their abilities to model a power system. All of them are kind of similar, but they have some advantages between each other. So let's go on with the numerical methods. So the first thing that we can do here to get to a solution, a numerical solution, it's that, let's say we have our problem and we want to, let's say we want to have a discrete representation of our dynamical system. Our dynamical system x dot equals f of x and t. So we're going to take some discrete time between some t0, an initial time of simulation, and a final time of simulation tf. And we're going to use some fixed step. So we're going to move from T0 to T1, from T1 to T2, from T2 to T3, up to some Tf and f minus 1 to Tf. So that step is going to be fixed for every interval, and there's going to be, we're going to call it h. Okay, h. That's going to be our step size. So of course we can write this down. T0, it's going to be, of course, T0. T1 is going to be T0 plus h. T2 is going to be T1 plus h, which is going to be the same as T0 plus 2h, and so on, up to Tf, which is going to be Tf minus 1 plus h, which is going to be, well, we have that, okay? So what we have done here is just take discrete steps, as many as we want, between the initial interval, the initial boundary of the interval T0 and Tf, okay? As I said, we can take as many points as we want. Okay, that's something that we're going to discuss throughout this chapter. Okay, so what we can do now, it's let's say consider that x of t k, or we're going to call it also xk, is the solution of x at time tk. Okay, so for this discrete model, this is the continuous model. Since we have a discrete time representation now, at some point tk, we're going to have some solution x of tk. That's what we're saying. Huh? That's what we're saying. So then the Taylor expansion of the next step of that k, so x of t k plus 1, which is going to be the short version of this is going to be just x of k plus 1, so we don't have to write the tk plus 1 all the time, around tk is going to be given by the Taylor's expansion. So it's going to simply be x of k plus 1. It's going to be x of k plus the first derivative evaluated at tk times h, the time step, plus 1 over 2 factorial, the second derivative of x evaluated at that time tk, times h squared, plus let's say higher order terms that than h squared. That's what this thing means. Higher order terms than h squared. So here, of course, we're going to have 1 over 3 factorial, the third derivative of x evaluated at tk dt 3h cubed, and so on, h to the 4th, and so on. We're going to have multiple values. So I'm going to direct this a little bit. Square. That's the thing. So now that we have these derivatives, we can express these things in terms of something that we already know. So we know that the derivative can be written in terms of this function f, which is, it's known, it's something known because you know the model of your system. So you know this equation f, this nonlinear, generally nonlinear equation f. Okay, so we're going to write it down like this, x of k. Remember that this is just x evaluated at time tk plus the function f evaluated at the k step, k x of k tk times h plus 1 over 2, the derivative of that f of xk tk respect to time times h squared plus the higher order terms, right? Higher order terms. So we have some discrete representation now for the solution of the system in a discrete time, right? For any tk time here in the middle. So what we can do with this representation is that we can use this information to approximate the solution. If we take all the terms, all the infinite terms related to that order of h squared and higher order terms, then we're going to have an exact solution. So this is when the handy things come up, you know. So if we take just the first term, the linear term, this one, linear term, then we're going to get some linear approximation from our solution, right? From our solution. So that's where the first, let's say number 1, let's go forward, Euler method, or FEM. This is where this thing comes from. So we're gonna approximate some x of k plus 1 equals x of k plus the derivative evaluated at some time tk xk tk times h. So this method, it's very simple, it's very straightforward. The only thing that you can do with this, remember, this is it's a vector equation. So let's say we start with some x0, right? We know that this thing is going to start from x of t0 equals x0. So this thing is known. The initial condition is known. So what we can do here, it's so x of 1 is going to be x of 0 plus f of x0 t0 times h. So we know that x0, we know that x0, we know that t0, and we know that time step, which is given for some simulation. If we use the small h, then we're going to have multiple points that we have to calculate to get a numerical solution, but we're going to have some good resolution of our approximation, right? But the thing is, since we know this one, we know this one, we know this one, and we know that function f that we can evaluate at those given points, then we can compute that x1, definitely. And then we go with this one. If we want to get the second step, right, we simply take that x1 that already computed, and we evaluate that t1 times h. And remember that this is for t1, which is going to be simply t0 plus h. That is going to be t1. And this is going to be the solution for t2, which is simply t1 plus h, right? t1 plus h. And we keep going with this up to x, let's say x of f, which is going to be x of f minus 1 plus f of x of f minus 1, t of f minus 1 times h. In this one is given for the final time tf, which is going to be simply t of f minus 1 plus h. So we can actually have a direct method. This forward Euler method, it's a direct method. I'll put it here. It's a direct method. Why? Because we only need the information from the previous step to compute the new step, right? So that is known at every step, and we have to use that information to get the new x of the new step. So it's pretty straightforward. It's a direct method, and it works okay in general when that h is small. But we're going to talk about that a little bit. 2. So the second method that we're going to look for is the so-called backward Euler method. BEM. So what's the idea with this backward Euler method is that it's also, first of all, it's also a first approximation. What it uses a first approximation of the Taylor's expansion. However, instead of using the slope at time tk, we're going to use the slope or that function f at the time tk plus 1, so the next one. So the difference is going to be just in that term, t of k plus x of k plus 1 is going to be x of k plus f now evaluated at k, x k plus 1, t k plus 1, h. That's the only difference. So one important thing to notice here is that this is an implicit method. Why? Because we have to solve for this one, but this x of k plus 1 also appears here, right? So we have to somehow rearrange this equation in terms of something that is known, which is known for the actual current time. So if we rearrange this thing, at this point in this general formulation, we don't know what that f is, but we're going to put some simple example here so we can follow up some general procedure. H equals x of k. So important note is that this one is unknown, and this one is unknown too. So we have to solve for that x of k plus 1. That's why this method is implicit, because somehow we have to get around this equation and solve for that x of k plus 1. So let's put some very simple example. Let's say we have x dot equals 2x squared plus 3, right? And with some initial condition, x of 0 equals, I don't know, 1. So let's say we want to have, of course, our x of 0, it's going to be just 1, and our x of 1, according to this method, it's going to be x of 0 plus this function evaluated at this x of 0 and, sorry, this x of 1 and t1 times h. So what that is x0 plus this f, which is 2 times x1 squared plus 3, all of this times h, right? So we're going to have x0 plus 2h x1 squared plus 3h. So we can now rearrange this equation, and we're going to have x1 minus 2h of x1 squared equals x0 plus 3h. And as you can see now, we have to solve for this x1. Somehow we have to solve here for this x1 equals this value that is known. So I'm not going to do it here. It's a simple equation, but we have to acknowledge the fact that that x1 is a variable that we need to solve for. So it's not that straightforward as the forward Euler method, where you can plug in the value at the previous step and get the new one easily. You don't have to do anything, right? So in this case, we have to solve for x1. Okay? We have to solve for x1. And as you can see from the right-hand side, everything is known. That x0 is something given, and that h is something that we know when we're computing some solution. However, that x1, it's something that we need to know. So the question here is, when we have a nonlinear system, in this case, it's just a one variable system and one equation. So we can use any numerical technique, just like Newton-Raphson, for example. Let's put here. one can use, for example, Newton-Raphson or Gauss-Seidel, for example, to solve this nonlinear equation. Okay, those are only two methods, but there are multiple of them that you can use to get the solution for this nonlinear equation. And as I said, this example is very simple because you have just one equation. In general, we're going to have multiple equations, n equations. And as you studied before, I think in chapter 2, this Newton-Raphson method, you studied that for power flow. Do you remember? Power flow. So you can use that same technique to solve for this equation or a system of nonlinear equations. You start from some initial condition and you approximate the solution using the Jacobian, right? That's basically the Newton-Raphson method in a nutshell, if you will. So the third method, which we want to use to improve upon the forward and backward Euler, it's what is called the trapezoidal rule method. Trapezoidal rule, TRM, and this is also an implicit method. So you can take this trapezoidal rule method as the average between the backward Euler method and the forward Euler method. You can say that. So it's simply basically the average between those two. So our x of k plus 1 in this case is going to be x of k plus let's say we're going to put it this way, f of x k tk times h. That would be the forward Euler method. We're going to add here f of k, x of k plus 1, t k plus 1 times h. Looks like a k, so I'm going to make it better. H. So if you get rid of this one, that would be the backward Euler method. So in this case, we're taking the average between those two. That is going to be the trapezoidal rule. So we're going to write it down one more time. X of k plus 1 equals x of k plus h half f of k xk tk plus f of xk plus 1 tk plus 1. And this one, just as we said, is an implicit method. Just like the backward Euler method, we have to somehow put this term, which is it's a function of x of k plus 1, to our left hand side and solve for this one, right? Solve for this one. So the same thing we have to do here. This term here, f, that depends on x at the step k plus 1, we have to move it to the left, and we have to solve that nonlinear equation resulting from this rearrangement. This thing we know this one, we know the h, we know the x of k. However, the next step, we have no idea what this x is, and we have to solve for it. So we're gonna add here just like the backward Euler method. the trapezoidal is an implicit method. We're gonna say we normally need to solve the resulting nonlinear system of equations at every step using, for example, Newton-Raphson. Okay, for example, Newton-Raphson. That's just one technique, as I said, but you can use that one since you already know. And it's a very good method. It has a good convergence when you start close to the actual solution. That's generally going to happen because the h or the amount of move that you have from one point to another is going to be fairly small because that h is generally going to be small. Something that you can ask about here, it's what's the normal value of h in this problems. That's actually a very good question. You normally start from T0 to TF, right? That's some period of simulation that you want to get. You want to solve those bunch of nonlinear equations, and you want to get some approximation of the solution so you can actually know what the dynamics of the power system are going to be in a certain amount of time. For power system, that interval is going to be from 0 to 30 or 60 seconds, around that. Okay. You can do more or less depending on what the study is going to be, but for, say, transient stability is going to be around that. Okay, around 0 to 60, 0 to 30 seconds. So a normal time step for that interval of simulation is going to be h around, let's say, 1 milliseconds, 10 milliseconds, around that. Around that. So you have some estimate of what that h is going to be and how you're getting your resolution of your solution. Okay. So to summarize what we have discussed this class are the general considerations related to why we need to use these numerical solutions. Basically, because of the large number of variables and equations and the nonlinear characteristic of the power system, we need to consider numerical solution. Those numerical solutions need to be stable and accurate. And in practice, there are a lot of commercial softwares, just like the ones that I described, but we're going to look for some numerical solutions to approximate our actual solution in a discrete way using the Taylor expansion. We came up with 3 methods, 3 of them related to the first order approximation using this Taylor expansion, which is basically neglecting all the terms related to order 2 or higher. Okay, so we use only the linear part. Of course, there are much more methods than this one. Next class, we're going to discuss another one called Runge-Kutta, which is a very well-known method to approximate, a numerical solution of a system of equations, differential equations. which is kind of similar to this one's, but it's is a fourth order. Well, it's an n order method. So, but the most common one is the fourth order Runge-Kutta. So we talked about the backward Euler method, which is an implicit method, and we need to every step we need to do something extra to come up with the solution. And finally, the trapezoidal rule, which is an average between the forward and backward Euler, is also an implicit method, and we use both derivatives of a time tk and tk plus 1. And since it's an implicit method, we need to come up for something extra to solve for this unknown variables. And this one is unknown too. So that's pretty much what we want to cover this this class. And next class, we're going to talk about some examples. So we're going to start with the example from the lecture notes, example 4.1. We're going to have some system x dot equals f of x, right? And we're going to solve it. We're going to approximate the solution using these three methods. Backward Euler, forward Euler, and the trapezoidal rule method. Those three. Okay, that's what we're going to do next class. Okay, if you have any questions, remember that you have my email here. So any questions, you're very welcome to send me an email. I will be glad to respond to you.